Hello everyone, welcome to lecture 9, that is on remote sensing data analysis. So, we will continue this. So, digital image processing. Digital image processing means the images that we acquire from the remote sensing sensors, that is basically a reflected emitted values, right. So, those are associated with the pixels. You can see here. So, these pixels are nothing but the array of digital numbers. So, when we see in the background, it is actually the DN values, which is further processed into the radiance and reflectance or emittance, right. So, these digital numbers, how do we process, how do we use them into our objective? So, we have to learn some basics, right. So, these are nothing but the processing of the digital images. So, when we talk about the band arithmetic, which is here, refers to the modification of an image for extracting particular features by transforming the values of each pixel using multiples of band. So, here we are using the multiples of band, these informations which is captured by your sensor, right, and they are used together to enhance one particular object or a target. So, band arithmetic process results in a new image from two or more images to highlight a particular object or target. It operates on individual pixel, not on the image average, because if the image is, let us say, 1 kilometer by 1 kilometer, right, and if we use the global operator, so then what will happen? This entire 1 kilometer by 1 kilometer, you are having only one object of this much size, right, which is not feasible, which is not practical, right. So, that is why when we perform this band arithmetic, it is operated on individual pixel, not on the whole image. So, there are few questions that we need to answer, then your doubts will be clear, you will understand more about the digital image processing, and especially when we talk about the band arithmetic. So, what could be the possible benefit of band arithmetic in remote sensing? Why do we do that, right? So, here the answer is to highlight a particular object or target, right. What is band ratio? So, band ratio is like other operation like difference, addition. Ratio is also one of the option that we can perform, right. So, if you have two bands of the same area captured by same sensor in different wavelength, right. So, if this is the target and you know the spectral response of this target, then you can use this lambda 1 and lambda 2 wavelength images together. If this is A, this is B, it can be A plus B, it can be A minus B, or it can be A by B, right. So, anything is possible. So, this is simple operation, but very powerful. It will give you more information about the target, right. Then the next question is, how can we perform ratio over a remotely sensed image? So, pixel by pixel, because here we are not considering the whole image, right. So, it has to be pixel by pixel. And how many bands will be required for the band ratio? So, here minimum 2, because you need something to do A plus B, A minus B, or A by B. So, if you have more, you can have A plus B plus C, or you can have A plus B minus C, or A minus B plus C. This type of arithmetic is also possible. You can also have A plus B divided by A minus B to normalize it, or you can have A plus C divided by A minus C. This kind of combination is allowed in band arithmetic when we use the remotely sensed images, right. So, here this will give you more idea about why actually we go for the band arithmetic and how it is enhancing the object, right. So, let us say when we talk about two objects and essentially they will have different spectral response, you can see here, then only we are identifying them based on their characteristic absorption features, right. So, here this one is vegetation and this one is the concrete, right. And here you can see between 0.4 to 2.5 micrometer, what is the response of a vegetation? Here if you consider the same wavelength, so it will be from here to here, right. So, this is for the concrete. Now, if you compare these two from here this much, right, compare only this much, then you will be able to easily notice that both are having different spectral response. So, here one absorption feature is coming, one is here, right, another one is here. Here you have 1, 2 and 3 very characteristic. Now, here when we talk about the band arithmetic, we also try to keep the highly reflected areas in mind. So, if you consider this vegetation spectra, so this is one absorption feature, this is one peak, right. So, if we do this ratio, we will get more idea about this vegetation, because all other objects will have different spectral response, right, if you compare them. So, if you do this ratio, only vegetation will get highlighted, right. So, that is the basis of this band ratio. So, pixel by pixel comparison between different images will highlight the difference very effectively. So, that will highlight the difference between concrete and vegetation. Similarly, any other object or target can be considered in this, right. So, this is one way of extracting the information from remotely sensed image, that is band arithmetic. Now, arithmetic band operation like difference, ratio and combinations are commonly used. I told you A plus B, A minus B, or A plus B plus C, or A plus C divided by A minus C, anything is possible here depending upon the spectral response of the target. So, how do we design it, right? A very common operation is band ratio. So, here band Mij, band Nij. So, here this is the band number and this is the pixel location, because it has to be pixel by pixel, right. So, when we talk about this band ratio, we should have minimum 2 band M and band N, that is the minimum requirement, and it should be pixel by pixel. Now, this graph can explain you or give you more idea about how do we design a particular indices. This graph will provide you more information about how do we design a particular band ratio, which is also known as indices, right. So, this is one absorption feature, this is another one, this is one, this is here. So, as I mentioned earlier, the peak will also be considered while designing the band ratios, right. So, minimum and maximum value both will be considered to design or highlight a particular object. So, when we talk about this, let us see a vegetation spectra, because the absorption features are very characteristic and it will be easy to understand. Now, here when we talk about vegetation, one peak is here, another peak is here, right, and the absorption features are here, here and here. So, if I have to design, I have to consider this location and this location, right, and if I do this ratio, what will happen? We will get the information about this vegetation, clear. So, that is the basis of band ratio designing. So, band ratio, it can be a combination of band differences, ratio and additions, right. I told you A plus B divided by A minus B, that is also possible. So, here you will normalize the ratio. When we talk about the gypsum spectra, the characteristic absorption features are located at 1700, 2210 and 2440 nanometer. So, if you see these absorption features, we can have the band ratio using these location and one of the peak reflected areas, right. So, when we consider this Landsat 7 ETM plus data, band 5 is having this wavelength range, band 7 is having this, right. So, band 7 is capturing this particular absorption feature and band 5 is capturing this peak. So, if we consider these two, we can design this gypsum index. So, here it is 1650 divided by 2220 nanometer, right. So, if you use this, all the gypsum pixel will be highlighted and the resultant image will be a ratio. Input is 2 bands, right, but output will be one ratio image, and that image, the brighter pixel will highlight the presence of gypsum, right. I hope this is clear. We will take another example, which is a very famous index, which is called NDVI. This normalized difference vegetation index. The formula is infrared band minus red band, infrared band plus red band, right. So, here these two are divided. So, this is a normalized index, this is a normalized ratio. So, here when we see this particular region, this is the highly reflected region. So, this is infrared, right. And when we talk about red, red is having this absorption feature. So, when we are having these combinations, basically we are trying to capture the minimum and maximum value that is produced by the target, and here the target is vegetation, right. So, in this case what will happen? You will have the ratio, and then the ratio again it will be a single band image, and the ratio image, the brighter pixel will have the vegetation, right. So, the image which is resultant of this NDVI, that is ratio image, and it will be a grayscale because it is a single band image. So, the brighter, the white pixels or which are very bright, those are vegetation pixels, right. We have one example which is Landsat 7 data only, right. So, here you have the standard false color composite. So, easily you can see these are the vegetations, right. These are the vegetation pixels wherever you are having the red color or dark red color, and these light red, those are sparse vegetation, but still they are vegetation only, right. When we consider the inputs, the infrared and the red band. So, here this is the infrared band and this is the red band. So, in the red band, basically if you remember the vegetation spectra, in the red band we are having the absorption feature, right. So, the darker pixel here will be representing the vegetation, but some other target may also be having the absorption feature here in the red, that is your water, right. When we consider the NIR, where we expect the vegetation is having the very high reflectance, right. So, in this case the brighter pixels are basically representing your vegetation. So, we are going to use them in this equation, and then we will have the ratio image. Now, remember this infrared band can be band 3 of Landsat, band 3 of some other sensor, band 2 of some other sensor. So, when you are having this NDVI calculation, you should be very careful while assigning these band number 2 or 3 as infrared and red band. Only the wavelength is mentioned here. So, the wavelength can be mapped with your sensor band designation and what wavelength they are using to capture the images, right. So, once we have this, then we will be able to produce this NDVI image, and here as I said, the brighter pixel will be representing your vegetation. So, the NDVI result in high values where IR dominates over red wavelength, right, that is the normalized difference vegetation index, strongly highlights the green vegetation portion of the image. This happens because green vegetation has a very high reflectance value in the IR region. The value of NDVI ranges between -1 to +1. So, this is a ratio which is ranging between -1 to +1. This is the value range, right. Widely used in agriculture, forestry and biomass estimation application, and it can also be used to study the crop health and growth. Why? Because this characteristic absorption feature which we are getting in this red region, right, and in IR we are having this high reflectance. So, these represent the health of the vegetation. So, what happens when we are having this kind of a spectra? This is also vegetation. I hope you are able to see this. This is also vegetation. So, shift in this slope from here to here, that indicates the health of the crop or the vegetation, right. So, this is widely used in crop health and growth. This is called red edge, right. So, you can refer to some of the standard literature and you can use them in vegetation related studies. Another example is normalized difference water index, generally used to identify the presence of water in an area, even including the plant water content. It is very useful in estimating flood, water stress or even drought condition of an area, because this will capture the or this will highlight the presence of the water on the surface. Another example is normalized difference snow index. It is the normalized difference of two bands, one in the visible and one in the near infrared or short wave infrared parts of the spectrum used to map snow. Here we are using the green and SWIR bands to calculate this NDSI. This is normalized difference snow index. Now, one thing I would like to mention here, that when you are trying to capture the images, we are also having the impact of or the influence of atmosphere, right. So, when we are doing this band ratio, this is band A divided by band B, right. So, here when we consider this band A, this is also having the atmospheric effects. This band B, that is also having atmospheric effect, because those are captured at the same time by the same sensor. So, when we are dividing them with each other, what is happening here? We are removing the effects of atmosphere. So, the band ratio, the resultant image will not have the impact of atmosphere, it will get cancelled, right, because both the bands are captured by the same sensor at the same time. So, that is one of the advantage of band ratio, that when we are trying to identify any object or material, at the same time we are also removing the effects of atmosphere or any other errors which are available in or introduced in your data while acquiring them. Now, we will move to image classification. This is one of the very important concept which is used to generate the inputs for our analysis, right. So, when we talk about the remote sensing, we try to generate the inputs for our decision support system. Or suppose if we are going for landslide related studies, then we need several parameters. So, remote sensing can provide you parameters which are captured from the space, which were not possible or which were not easy to capture in the field, right. So, these are the processes, or the image classification is a process by which you can generate your inputs for your analysis, right. So, we will try to understand what is image classification. So, image classification is a process by which we assign pixel to a particular class or category, right. So, remember we have this image, and initially when we captured them we had this dn, then we converted to radians, then we converted to reflectance or emittance. So, let us say now we are having the reflectance value, but these reflectance value are arranged in such a way that you are able to see the image, right. You are able to see the image here, but you will not be able to quantify immediately if I ask you to tell me that how much area is covered by a lake or by a forest or by urban. So, what we do is, in image classification we try to assign a class or category to each of the pixel of my image, so that immediately I should be able to tell what is the area, right. What is the area that belongs to lake, forest, urban area or water body, that can be easily identified, and then we will be using those information into our further analysis, right. To assign each pixel of the image to a particular class or category, a relationship needs to be established between the data and the category. Now, let us say this is a particular image, right, and from the field we know that this particular pixel belongs to forest, this belongs to water. And how do we know that? Because each of the pixel is having x, y and z values. So, x, y is your latitude, longitude, and z is basically your dn value or reflectance or radiance, whatever it is, right. So, when we are having the location value, we can use the GPS, we can track that particular pixel where it is on the ground, and then we will see whether it is water or whether it is forest or whether it is some other class or category. Once we have that, then we can collect such information in the field that all these pixels belong to water, right. So, if we know for water latitude, longitude, these are the latitude, longitude which belongs to water from the field, right, and from the image we will also have the dn values or the reflectance value. So, let us say R1, R2, R3, all these are different reflectance value from the image, right. Now, we have a set of values representing water. Similarly, I will have set of values for forest. Similarly, I will have set of values for urban and any other class which I want to classify my image, right. So, likewise you have to collect, or you should have the information from the field that these are the class or category which are available in my image, and then you should have the information about the corresponding reflectance or dn values from your image, right. So, this classification is grouped into two major classes. So, the first one is the object based, here it is based on the geometry, right. So, when we talk about the geometry, that means your spatial resolution should be very, very high, right. In other terms, we call it fine resolution. So, when we talk about the high spatial resolution, that means the pixel size is very, very small. It should be in centimeter, millimeter, or maybe few meters, right. So, then we can do it with the geometry. So, we can use the geometry as one of the training parameter to classify my image, but most of the time we are having the moderate or coarse resolution images, right. So, in that case this pixel based classification is done, and here we are using the DN values, not the geometry. Geometry is used in case of high spatial resolution. So, pixel based is good for medium to coarse resolution data sets. Now, we will try to understand this image classification. So, when we have the remotely sensed image, these images are captured in several bands and they are using different wavelengths to generate these images. So, each image is having a spectral response of a material or target in that particular wavelength. When we try to extract this information, we have the spectral curve. If you remember, the spectra we are able to generate. So, when we talk about the panchromatic, we have single values. When we talk about the multispectral, we have few bands, minimum 3 is required, but we can have up to tens of bands. So, those 10 values will be used to plot our graph for a particular pixel. When we are having the hyperspectral, we are having high spectral resolution. So, more number of points are there and those are used to plot the graph, and they will have more characteristic absorption features of the target. So, utilizing this spectral information, right, how the material is behaving in different wavelengths, we will be able to classify our image. So, this is pixel based, where we are going to utilize the DN values, right. Now, we will see one by one. So, there are two major classes. First one is unsupervised, another one is supervised. So, let us understand this unsupervised first, right. So, this multispectral image, we are having 1, 2, 3 and 4 bands, and now these are nothing but the array of this digital number. So, we are having 4 data matrix, right. So, these 4 data matrix will be used to plot into n dimensional space, and this ND is equal to your number of bands, right. So, when we try to plot this band 1 versus band 2, then we will have few clusters, right, because similar object will have similar digital number or reflectance or radiance or maybe emittance, and that will be used to generate this kind of cluster. So, when we are having this clusters, when we have plotted band 1 versus band 2 versus band 3 versus band 4, and also in the n dimension, right. So, together they are coming. So, all other bands are in the background. So, when we talk about this first cluster, it is representing a particular class or category, right. So, this is, let us say, class 1, this is class 2, this could be class 3. So, here all the pixel which are in this particular cluster, they will be named as class 2. This is how we are going to provide class or category to each of the pixel of this image, right. So, this is called classification. Now, after classification, we also need to validate whether our processing, our classifiers have worked efficiently and produced the correct classes, right. So, what we will do? We will go to the field, we will collect the different class or category information in terms of their latitude, longitude, and then we will try to identify those pixels in which classes actually my classifier has classified them into, right. So, if suppose class 1 is mistakenly classified as class 2, so according to this algorithm it is giving class 2, but actually in the field it is class 1. So, that is the error associated with my classification. So, what we do? We use the ground information and then we try to estimate the accuracy of this particular process or the image classification, and then we will say that my classification is 60% correct, 70% correct, or maybe 90% correct, right. Now, here this was the case when we were talking about the unsupervised, when we did not have any input while classifying them, right. So, in unsupervised classification, we did not supervise this particular classifier. So, the classes were given by the system itself or the method itself. But when we talk about the supervised classification, here the supervised means supervision is required. You will train the algorithm based on the ground truth, and those ground truth will help the method or the technique to train, and then it will give you the class or category. How? So, the training areas. So, the pixel information which is collected here while doing the ground truth. So, here it was used for the accuracy assessment, but in the supervised you will be providing them to train the algorithm, right. And this particular set of values, let us say this is forest, right. So, this will be overlapped here, and then it will extract the corresponding DN values of all the bands, and then it will make a cluster and it will say this is forest, right. Similarly, for all other classes, similar relationship will be developed between the field and between the DN value or reflectance value. So, once you have this kind of clustering, then again you will have the forest, and this is your maybe water body or maybe, right. And then again you will have to assess the accuracy of this. So, remember the same points which you have used here for the training the data should not used for the accuracy assessment, that we will discuss in the further slides, right. So, we have learned we have unsupervised and then supervised classification technique. The same thing is explained here. So, here we are having this pixel, and for this pixel we are having all these values from different bands, right, and these pixel values will be used to classify this image. I hope you understood this. So, here we are having 5 bands. So, these 5 values are extracted, and this location was identified based on the field information, whether it is forest, water, or maybe urban area. So, all these classes will have different set of values from this pixel and from the ground information, right. So, this is training, then here we will do the mapping. So, this is classification, this is output, and then we will go for the accuracy estimation. So, we will continue this in next part of this lecture. So, thank you very much for listening, and we will have the part 2 very soon. Thank you.